Good afternoon, students. Welcome to the lecture of Real Analysis 2 in your first year semester 2 course. In the last semester, we have studied 5 theory papers, 2 practical sessions with 1 seminar. The theory exam is being completed. Now we are entering in the second semester. We will first discuss what is the structure in our semester 2. Okay. In semester 2, we have 3 hardcore theory papers. Hardcore theory means these are the compulsory theory papers. There are 3 compulsory papers: Algebra 2, Real Analysis 2 and General Topology. No doubt with a system of 80-20 pattern. Okay. Then we have 2 soft core theory paper. Soft core theory paper means these are the optional papers, and among these 2 optionals we have to select one. But in our department we were running this paper of complex analysis. Therefore we were conducting this as a soft core theory. Then we have to go for an open elective theory. Okay, this open elective theory paper, fundamentals in mathematics in Swayam course, these two we were offering to the students of non-mathematics department, right? That is to this other department in our school, right? Therefore your structure for this semester will be: there are 4 theory papers of mathematics, 1 theory paper open elective. We have selected either from office automation or from statistical method. Okay. Then we have 1 practical, practical 3, which is latex beamer. This latex beamer is actually a next part of the latex which we have studied in our previous semester, and is of 50 marks, 40-10 pattern. That is 40 marks for university exam and 10 marks for the internal. Then the next practical, which depends upon the open elective theory paper you have selected. That is, if you have selected office automation as your theory paper, then this practical OEP 2.1 will be according to your paper. Or if it is a statistical method, it will be, the practical will be based on your statistical method. These 2 papers were run by respectively Department of Computer Science and Department of Statistics. Is that okay? And we have the seminar for 25 marks. Now in 1 or 2 days we will distribute you the seminar topics, and you have to make the preparation, and accordingly we will conduct the seminars on every Saturday as we have conducted in the last semester. Okay, this is what your structure. If you have any difficulty in your structure, you can ask me. 3 compulsory paper, 1 optional paper, means there are 4 theory papers of mathematics. 1 open elective paper you have selected. 1 practical on latex beamer. 1 practical on your open elective. Okay. Therefore, this will be total for 480 marks. University exam 145 marks. Internal total it will be a 625 marks. That is 25 credits. Right now, these are of 25 credit. This is what a structure of your semester 2 in MSc 1 course of mathematics. Okay, I hope the structure is clear to everyone.
Yes, ma'am.
Hello, am I audible, students?
Yes, ma'am.
Yes, ma'am.
In between, I lost the network actually. Okay, what I am discussing is in real analysis 1, we have found the integration of a bounded function defined on the closed interval a to b. Correct, no? But the question is, if we replace this bounded in closed interval by any arbitrary set, that is, say, set of positive integers, negative integers, or rational number, whether we can find out the integration with a similar Riemann integration method? What do you think? Can we do this? Yes, students, you have to answer me. Okay, actually, if we take that closed interval, what the method we were using for Riemann integration? First, we were partitioning this, no?
Yes, ma'am.
Yes, ma'am.
We are finding the partition, then we were finding lower sum, upper sum by finding the infimas and supremas of the corresponding functions on those subintervals of the partition, and then checking the value of upper integral, lower integral, and if these two are equal, then only Riemann integration holds. But the question is, if I replace that bounded interval, closed interval, by an arbitrary set, the question arises how to make the partition. Correct? No, as it is the set on the real line, we were making the partitions. But in this case, it is not possible to make the partitions. In this, that's why there is a need to have a generalization of the Riemann integration. And this generalization of finding an integration on an arbitrary set was firstly introduced by a mathematician Lebesgue and hence called as the Lebesgue integration. Before that, we have to see what is Lebesgue measure, outer measure, etc. Okay. Therefore, this wallpaper deals about the Lebesgue integration. Okay. Now, let me just go for sharing my screen. In today's lecture, we will discuss some basic notions which are helpful to understand the real analysis 2 paper. Check, is the screen visible to everyone?
Yes, ma'am.
Yes, ma'am.
Good. Now we will start with some basic definitions. Okay. One by one, I will write the definitions. You have to tell me the definitions. Okay. First definition, what is set? One today we will take only some introduction basic concepts, because once we understand the basic notions very clearly, then only we can understand this Lebesgue measure part smoothly, right? What is set, you know?
Collection of well-defined objects.
Yes, this is well-defined collection of objects. I am not writing the whole statements, I'll just write in short. Okay. Well-defined collection of objects. Can anyone tell me the example of not a set? Example of set we can tell us many. In mathematics also, in day-to-day life also. What about an example which is not a set? What do you think?
Set of heighted students in MSc1 class.
Yes, set up all heighted students in this one class, set up all beautiful girls, set up all scholar students, right? Like all these are the examples which is not the well-defined collection. This is not a set. Now, if once we write set, rest things we can write, I think. Na? What are the definitions related to set? Subset, superset, etc. Right now? What is subset? Suppose A I am writing as a subset of some yes. How can I define this? A. This is a collection of X such that X is in yes. Right? No?
Yes,
Yes,
ma'am.
ma'am.
Okay. Some elements. Okay. Now the subset may be defined in two ways. Proper subset and improper subset. Correct now? Proper and improper. Next we will go to the operations of the sets. What are the operations? What are the operations on sets defined? Yes. If we have two sets, say A and B, how many
Union,
types?
intersection.
Good. First is union. What is union? This is denoted by a symbol A union B. How you are going to define the set? How you are going to define the set? Union of the two sets. Hmm. Actually, in union, which elements we were collecting? All the elements in A and B. Okay, but we were not writing the repeated elements. We are writing the repeated elements only once. Correct? Now, what
X
is
is
the
such that
mathematical X
X is
such
such
that?
that X belongs to A or X belongs to B.
Good. X belongs to A or X belongs to B. Right? Next, what about intersection? Denoted with this symbol. How can I define
X
this?
such that X belongs to A and X belongs to B.
Yes, it is and. X is in A and X is in B. Therefore, the element should be in both the sets A and B. Here, this element can be in any one of the set. This is what a intersection is, right? What about a complement? Because in wallpaper we were dealing with sets only, sets and their operations. Okay. For writing a complement, what I will write? For a set A, let me write some universal set S say. Let me write some universal set. Correct na? If I want to write a complement, I first should define the universal set. Okay, how should I define the complement? What are the symbols? There are many symbols. Correct na? So in some book it was written like this, complement. Or in some books it is A tilde. Or in some books it is A bar. Right no? We
Yes,
will
ma'am.
follow this middle. Right? How can you define this?
X such that X belongs to S and X does not belongs to A.
X such that X is in yes and
Yes, and
X
X
is
does not belongs to A.
right. X is not in A. Right? Next, how can I write the difference? A minus B. The notation is in some books it was A like this also tilde. Hmm. Yes. Which elements are there in this? The elements in A which are not in B. Correct, na?
Yes, ma'am.
Hmm. Therefore, this is X such that X is in A and X does not belongs to B. Clear, no? Is there any is there any problem with this definition?
No, ma'am.
No, ma'am.
Good. Next is symmetric difference. Can anyone know what is a symmetric difference? Symmetric difference is denoted with this triangle shaped symbol. A symmetric difference B. Okay, and this is defined actually as A minus B union B minus A. This is called as symmetric difference. First we will take the elements in A which are not in B, then the elements in B which are not in A, and then we will take the union, and this is called as the symmetric difference between the two sets. Okay, these are some of the operations we were going to look as the upon the given sets. Okay, now upon the sets we have studied some important laws also. Okay, what are the laws we have studied? Do you remember distributive laws?
Yes, ma'am.
Yes. Can anyone tell me the distributive laws?
A union B intersection C equal to A union B intersection A
Very
union
good.
C.
A union B intersection C is equal to now.
A union B
Hmm,
intersection A union C.
good. What is one more? A intersection now. Hmm. What is this? A intersection
A
B means is
intersection B.
hmm,
Union
union.
A intersection C.
Okay. These are the laws known to us, right? If I ask to prove this law, can you prove? Hmm? Can you prove these laws? You have studied the proof somewhere in 12th standard, I think. Right now?
Yes, ma'am.
But if I ask to prove you now only, can you prove this? How to prove if I want to show both the sets are same? What is the methodology we were proving, we were using in order to prove the two sets are equal? If I want to show A is equal
A
to
is
B,
subset of B and B is subset of A.
good, A is subset of B and B is subset of A. And to prove this statement A is subset of B, we will start with an arbitrary element of A and we will show it is in B. Correct now? But this is today's homework. Okay? You have to give the proof of the distributive laws. Okay? What is one more law you have studied related to the sets? Starts with D again.
De
De Morgan's
Moivre's
law?
law.
No, De Morgan's laws. De Moivre's is for the trigonometric ratio, no? Cos theta plus I. I am asking about the sets. Okay, what are De Morgan's laws? Do anyone remember? This is in connection with the complement, no? What is A union B complement? What is A union B complement? Yes? I hope I am audible.
Yes, ma'am.
What is De Morgan's law? Forgot? I think you
A
have forgotten
complement
that.
intersection B complement.
Yes, this is A complement intersection B complement. Or one can write it in other notations A union B. This bar complement. A bar intersection B bar. What is one more De Morgan's law regarding the intersection? A
Union.
complement union B complement. Correct, no? These laws we were going to use it actually or in the next concept. Okay. Now we will write some properties regarding the empty sets. Okay. Suppose we have two sets. Suppose we have two sets in our hand. One is empty and other is some x. Other is some A. I will write. A is the symbol I am using. Let me write A only. Okay, no. Okay. Now I'll ask you some questions on these operations on these two sets. What is A union 5?
A.
A
A.
itself.
What is A intersection 5?
5.
5.
This is 5. Right now? And if suppose A is a subset of the universal set. Okay. Let me include in this only. Then what is A union X?
X.
X. What is A intersection X?
A.
A.
Yes, it is A. Okay. One more. Suppose I have empty set. I have two sets, empty and X. Okay. Then this is a universal set. Say this is my I think you know the concept of universal set, no? Then what is phi complement?
X.
Yes, it is X. What is X complement?
Phi.
Phi. Okay. What about X double complement?
X itself.
X.
X itself. Good. Okay. In case of a general set, what is A intersection A complement?
Phi.
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 Right? What about A union A complement? Universal set I have taken X.
X.
Universal set is X. Is that okay?
Yes, ma'am.
Regarding the sets, very simple notions I am taking today. Okay. Now what we will do, just whatever the De Morgan's laws and distributive laws we have written, in case of two sets only, can we extend to an arbitrary union and arbitrary intersection as well? Arbitrary. Okay. Let us try to understand what is arbitrary intersection. For this, what I will do, I will use a notation curly C as collection of disjoint sets. Collection of disjoint. What is disjoint set?
Set having no common elements.
Intersection is empty, right? No? Intersection is empty, no? Intersection of these two sets is empty. No element is in common. Okay. And suppose we have the subset, say AIs in C, in this curly C. In this curly C. Then what about the arbitrary intersection or arbitrary A? A is in C. No need to write AI, no? Correct, na? What is arbitrary intersection then? Arbitrary intersection of all the subsets of C we were taking. Therefore, these are the elements X such that as we have defined for the intersection of two sets, similarly we have to define for the intersection of arbitrary, some A1, A2, AN. Suppose I have the elements to be sets to be A1, A2 to AN in curly C. What is curly C? Disjoint collection of sets. Means all these are having the, all these sets are the disjoint sets. Then if I want to define their intersection, arbitrary intersection, what it will be? This is finite intersection actually. I from 1 to n. How you are going to write it? This is the collection of all X in the universal set X, one can say, such that, yes, X is in AI for all I, right now?
Yes, ma'am.
X is in AI for all I. This is a finite intersection. Now I am just going to write it for the arbitrary intersection. Arbitrary intersection means what? This intersection is of infinite number of sets, right? No? The word arbitrary means. So here also one can write X belongs to the universal set, say X, such that A is in C implies X is in A. A is in C, X is in A. Means for every A, the X should be an element of A. Correct, na? Okay. Now let us go to write the De Morgan's and distributive laws in case of arbitrary union and arbitrary intersection. Therefore, let me repeat De Morgan's laws, because in our study we were not going to take only for the two sets. The whole discussion is based on the arbitrary intersection, arbitrary union, finite intersection. Arbitrary De Morgan's laws for arbitrary union intersection. Okay, are you getting the meaning of the word arbitrary? Yes, infinite
Yes, ma'am.
intersection. In short, it is infinite union or infinite intersection. Okay, then yes, complement of union A is in curly C A. This is complement of arbitrary union. What it will be? Complement of arbitrary union of A, where A is in the disjoint collection. Therefore, may I write this to be intersection A is in C node of A complement. No? Right or not? Arbitrary union is being converted to arbitrary intersection, and we are going to take the complement of every individual set. This is very similar to the De Morgan's laws we have written in case of two sets only. Right now, union we have changed to intersection, and we have taken the complement of every set. Right now,
Yes, ma'am.
here also we have done the same thing. In case of arbitrary union, complement of arbitrary union, we have changed this union to intersection, and we have taken the complement of every set involved. Okay, same thing we are going to write it for arbitrary intersection. Arbitrary intersection of A is in curly C of A is. What it will be now? This is union. No doubt A is in curly C, and this is complement A. Right now?
Yes,
De
ma'am.
Morgan's laws for arbitrary union and arbitrary intersection. Now let me write De Morgan's laws, sorry, distributive laws also for arbitrary distributive laws. Okay, how I am going to write the distributive laws? Suppose I am going to take B intersection. Now here I am taking the union of arbitrary collection. So this is union A is in curly C. Okay, then what it will be? Let us recall what is distributive laws in case of two sets. If we were going to take A intersection with some union, then actually this is union of the corresponding intersections of the set with the two elements. Right now here also I will take intersection. I will take B intersection. Therefore, I will take union. Union of what? Union of this B with every element. Correct now? B. Sorry. Union I have taken. Now I have to take intersection. Sorry. B intersection A, where A is in. Correct or not?
Yes,
You have
ma'am.
to compare this with case of two. B intersection A union C. How we can write it? Yes. How can we write it? B
B
intersection A union
intersection A union B intersection C.
Section C.
Yes, B intersection C. What we have done, whenever we were finding intersection of B with this set, we have taken the union. Union of what? Union of intersection of B with both the elements. Right now, once intersection is taken with A, once it was taken with C. Right? These two. And we have taken their union. That is what we have done. First, we have taken the union of what? Intersection of B with individual element. Correct now? I hope idea is clear. Similarly, how can I write B union intersection A? A is in curly C. Yes? Now you have to tell me. How can I write this?
Intersection.
Intersection A is in C of what?
B union
B
A.
union A.
A.
This is B union A. Okay. Is the point clear up to this?
Yes, ma'am.
Yes, ma'am.
Okay. Now we will go to next point. Countable set. Yes. Can anyone define countable sets? Because this is the most used word in real analysis too. Therefore, you should be clear with the meaning of this countable set. What is countable set? See,
The
whatever
set
you
which
know,
is similar to natural numbers.
similar is the word. I think the word similar is not suitable here. Correct?
Equivalent.
Yes, it is equivalent. Okay. But can you answer me a question? If it is a finite set, say, let me change the color. Suppose I am writing this as a finite set. What is your idea whether it is countable or not?
Yes, ma'am, it is countable.
But can you prove its equivalence with natural numbers? Is it possible?
No, ma'am.
No, then how
But
can you show
one
it?
corresponds.
One correspondence you have to show, na? See, this is my natural number set. 1, 2, 3, and so on. And to the left side, I have only 5 elements. Can you show the one correspondence? One correspondence holds with only up to 5 elements. Huh? What is one correspondence? The word. What is the meaning of one correspondence? Let us make this point clear first. Two sets A and B are said to have the one correspondence when. What is one correspondence? You have used a word, na? One correspondence. This is just a discussion session. You can answer very freely.
Every element in A, there are image in B. Unique image in B.
For every element in A, there is unique image in B. I think you are giving the definition of function. No doubt, the one correspondence is a function. But what are the properties possessed by the function so that it becomes a one correspondence? Getting my question? Yes?
1, 1 and 1, 2.
Yes, very good. The function should be 1, 1 and onto. The function should be 1, 1 and onto. If I want to tell you exactly, suppose this is set A, this is set B. Let me show you with the help of Venn diagram. And there is a function f from A to B. Suppose I have 4 elements, 1, 2, 3, 4. And there are 4 elements again, A, B, C, D. Okay, then what is 1, 1 onto? 1, 1 means for every element there is one element in B. Right now? And what is onto? Range is equal to codomain. That is, every element in B has a unique pre-image. Correct now?
Yes, ma'am.
Therefore, 1, 1 onto means this is the case. For every one element in A, there is one element in B. 1, 1 onto. This is called as a 1, 1 correspondence. Whenever this situation holds, then the two sets are said to have the 1, 1 correspondence. Now, in case of countable sets, we were finding, suppose whatever the set is given to us, A sets, we want to check whether the set is countable or not. Then we were checking its 1, 1 correspondence with set of natural numbers. Why with natural numbers only? Can anyone tell me? Why not other set? Why not set of real numbers? Why not set of rational numbers? Why only with the set of natural numbers only?
Natural numbers start with 1.
It starts with 1 actually, or it gives us the systematic method of counting the objects. This set is used for the counting of objects, no? 1 object, 2, 3, 4, and so on. Okay. Therefore, whenever I am saying countable, okay, whenever I am saying countable, therefore we were using the set natural number which helps us for counting. Which helps us for counting. Therefore, what is the exact definition of a countable set? A set is either empty or finite. A set is either empty or finite or having one-one correspondence with set of natural numbers. With set of natural number. That's why the first question is, this is countable. Correct, na? Because it is finite. All finites are countable. Can you count it or not? First element, second element, third, fourth and fifth. I can count the number of elements. Therefore, this is countable set. Okay? This is finite rather. Okay? Therefore, empty is countable, finite is countable, and those infinite sets which has one-one correspondence with the set of natural numbers is called as a countable set. Is the definition clear?
Yes, ma'am.
Yes, ma'am.
Okay. Or in other words, one can write the definition to be a set is countable if it is the range of countable, or the another word, do you know the another word for countable? Denumerable it is. Countable or denumerable if it is either empty or the range of a sequence. Now let us check whether the two definitions are same or not. Whether the two definitions are same or not. What do you think? Same or different? Range of a sequence means what? No doubt they have made it clear that empty is countable. The second condition imposed is empty or the range of a sequence. Okay. Now we know the fact there are two types of sequences, finite sequence and infinite sequence. What about the finite sequence? No doubt sequence itself is a function. Right now, sequence itself is a function where the domain is. If it is a finite sequence, this should be a finite set, but in general we were writing this as M to R. Correct now?
Yes, ma'am.
Sequence is a function from set of natural numbers to set of real numbers. If the sequence underlined sequence is finite sequence, what is the range of that finite sequence?
Finite.
Finite. Range of finite sequence is finite. Therefore, that finite set is a countable set according to this definition. Right now? And if it is the range of infinite sequence, then also it is countable. Why? Because as it is the range, let us say the range of this f from n to r is f of a, correct? Sorry, f of n, no? F of n. This is the range, no? For this function. Correct? Then if I consider the function like this, may I say this function gives me 1 1 ontoness? This is the
Yes,
1 1
ma'am.
ontoness. And this 1 1 ontoness is with which set? With the set of natural numbers. Okay. Therefore, either you call this as a range of a sequence, or you can call 1 1 correspondence with the natural numbers, one and the same thing. Therefore, what is countable? Every empty is countable, every finite is countable. And in case of infinite set, two definitions we have in our hand. What are the two definitions? Either it should have a 1 1 correspondence with set of natural numbers, or It is the range of a sum sequence. Correct na? This is the range of a sum sequence. Whenever we were writing the range of a sequence, what kind of statement we were writing? Say S1, S2, S3, dot dot dot, Sn and so on. Right now, this is the range. And no doubt, this we can have a one correspondence with set of natural numbers. That's why, in case of infinite sets, we can use two criteria for the countable set. One is with, what is one? One correspondence with set of natural numbers, or it is equivalent to say this is the range of a sequence. This is the range of a sequence. Yes or no? Clear with the definition or not? Is the definition?
Yes, ma'am.
Good. Can anyone tell me the examples of countable and not countable sets now? Countable, not countable. Both you have to tell me. First, let us make clear. Every empty is countable. Second, every finite set is also countable. Right now? Can anyone tell me other examples of countable sets, not countable sets? What about set of real numbers?
Uncountable.
Let me write the examples here. This is uncountable. Not countable or uncountable, one can write anything. Okay? Other examples? What about positive integer set? Z plus.
Countable.
Yes, it is countable. What about negative integers?
Countable.
What about natural numbers?
Countable.
Good. Natural numbers, countable. Okay. What about integer set, including both positive and negative?
Countable.
Sure.
Yes, ma'am.
Next, what about the closed interval 0 to 1?
Uncountable.
Can you prove it? I think you have studied the proof now in your BSc course. Whether you have studied the proof of this closed interval 0 to 1 uncountable in your BSc course or not?
Union of uncountable is uncountable.
No, you are telling me the proof of this in.
No, ma'am.
Achha, next point you are saying. No, I am asking you about the proof of this why closed interval 0 to 1 is uncountable. You have studied the proof or not? That is what my question is.
No, ma'am.
Not studied.
No, ma'am.
I think it is there in your BSc course. I think two of you are saying only no. What about other students? No one has studied the proof of the 0 1 is uncountable. Whether countable concept you have studied or not in your BSc course. Countable शिकलात का तुम्ही BSc ला?
Yes, ma'am.
Then how it is not possible to take this closed interval 0 to 1 is not countable? It was there. I think you might have forgotten this. So let me keep this again for homework. Today's homework. I want the proof of closed interval 0 1 to be uncountable as a homework for today's session. Okay. Now we will go for, I think Rutuja is saying about the operations. Right now? What about subset of countable?
Countable.
Series subset of countable is countable. What about superset?
Countable or uncountable?
It may or may not be. No, it's not sure. So we cannot predict about the superset, right now?
Yes, ma'am.
Okay. What about union?
Countable.
Union of two sets I'm asking, okay? Union of two countable sets. Yes, countable or not?
Countable.
Countable. What about intersection?
Countable.
Okay. Now one example I forgot now. Rational numbers. Here. Where
Countable.
should I write? Countable or uncountable? Yes? What about
Countable.
it is countable? You must see the proof also. Why these sets are countable. True and down. Okay? Here we have written union of two countable. Union of two countable is countable. Intersection of two countable. Now let me go for an arbitrary union and arbitrary intersection. What is arbitrary union? Or one can say countable collection of countable sets. Countable collection means what? Arbitrary. Infinite. Infinite union of countable sets. Yes?
Countable.
Countable or not? Yes, it is countable. I think you have highlighted the statement. Union of countable collection of countable sets is countable. What about countable collection, intersection of countable collection of countable sets?
Again countable.
No, you have to think on this. For intersection, you have to think. Intersection of countable collection of countable sets, you have to think. Okay, just think on this. Okay. This is what about countability. Next, I want to go for relations. Relation is also an operation on set, na?
Yes, ma'am.
Is relation? Suppose we have two sets A and B. Finite time we one can take. Yes, what is the relation then? Hmm. Yes, what is relations? Whether do you have today as a lecture at 1:30 open elective? Both classes. Hello?
No, ma'am. काही instructions नाहीत आल्या.
Yeah, I can complete this relation part. What is relation? Relation is a relation, right? No? What is mathematical definition? Relation is a subset of a Cartesian product, right? No? What is Cartesian product we were defining? Cartesian product is an ordered pair AB such that A is in A and B is in B. Correct? And the relation is a subset of this Cartesian product. That is, to every element A, there is one element B related to A. There is one element A related to, and there is one element B related to A. This is the relations. Okay. When this relation becomes a function, whether every relation is a function?
No, ma'am.
No, not every relation is a function. When the relation becomes a function, if every element in A gives us the unique image in B. Sometimes in relations, it is possible to have two different images of the element. Therefore, every relation is not a function. In order to be this relation to be a function, we should have a unique element. For every unique A, there is for every A there is unique element in B. Then it will form a function from A to B. Right? Now I want to just discuss the properties of the relations. First is reflexive relation. What is reflexive relation? Whether it was taken in other paper, algebra 2 or in other subject, whatever I am taking today, introduction.
टोपोलॉजी मध्ये झाले मॅम काउंटेबल वगैरे.
मग सांगा ना पटापट उत्तर द्या. Reflexive relation काय? Relation is said to be reflexive if
A is related to A itself.
A is related to A itself. Next, symmetric. Yes, A related to B.
B is related to A.
Implies B related to A. Third, antisymmetric.
A is related to B. B related to A implies A equal to B.
What is last?
Transitive.
What is transitive then? A related to B.
B related
B
to C
related to
implies A related to C.
One can have the examples also, no? One can discuss the examples from the relations, right? Can anyone tell me the example of a reflexive relation? Example of a reflexive relation. Suppose I am considering a class of MSc 1 mathematics and I am defining the relation as a friendship relation between two persons, between two students. Whether the relation is reflexive, whether a student is a friend of himself or herself.
Yes, ma'am.
Yes, it is. It has to be. Right now, we should love ourselves. We should be a good friend of ourselves. But the relation is reflexive. Whether it is symmetric,
Yes, ma'am.
A is a friend of B. Whether B is a friend of A, yes.
Yes, ma'am.
Yes.
In some rare situations, it is not. Right now, we were assuming some person to be a good friend of ourselves. But the person may or may not assume B as a friend, no? Right? Okay, therefore we will go ahead with positivity. Yes, it is symmetric. A is friend of B, then B is also friend of A. Next, whether it is antisymmetric, A is friend of B, B is friend of A, whether these two are same persons,
Yes, ma'am.
same. Suppose Rutuja is a friend of Simran. Simran is also a friend of Rutuja. Whether these Rutuja and Simran are same persons? You
No,
both were
ma'am.
answering my questions. No, that's why I have taken your names. Rutuja and Simran are not same person always. Need not be. Correct, na? But this is antisymmetric. This is not antisymmetric. Last, transitive. A is a friend of B, B is a friend of C, then A is a friend of C. We will go for positive situations again. Yes, it is a friend. I think on Facebook, this holds good, right now? Friend of friend is a friend included in our friend list. Always. Right now? Our friendship satisfies reflexive, symmetric, and transitive. Let us do it for enemies. Enemyship. Enemy of one another. A person is enemy of another. First, reflexive. A person is enemy of himself or herself.
No, ma'am.
No, it is not. It should not be. Right now? As I told you earlier, we should love ourselves. Therefore, this reflexive do not hold. What about symmetric?
Yes, it holds.
Yes, it holds again. A is the enemy of B, then B is also enemy. Again, there are two parts actually, if one may think. If some A is assuming B as an enemy, but it is not guaranteed that B should assume A as an enemy, no. But we will just
Yes,
go,
ma'am.
yeah, yes it is. But this is a doubtful whether symmetric holds or not. Right? Therefore, we will forget about symmetricity. Again, anti-symmetry do not hold, na? Anti-symmetry do not hold, right? What about transitivity? A is enemy of
Not hold.
B, B is enemy of C, A is enemy of C. Holds or not? Not hold.
A is friend of C.
A is friend. दुश्मन का दुश्मन दोस्त होता है ना? Right? No? दुश्मन का
Yes,
दुश्मन
ma'am.
तो दोस्त होता है, right? So this is just for your understanding I have taken this example. Okay. Now depending upon these relations, you can check many more mathematical examples as well. Depending upon this, we were writing the relations with two properties. First is partial ordering relation and equivalence relation. Okay. Then when the relation is said to be a partial order relation, do you know when the relation is said to be partial order relation? Equivalence relation, partial order relation. I think you have studied both of them. Yes? If a relation satisfies the three property RAT, reflexive, antisymmetric, and transitivity, the relation is partial order relation. And if it is going to satisfy RST, that is reflexive, symmetric, and transitive, then the relation is said to be a equivalence relation. Now, this equivalence relation is the word we have used many times. Correct, na? We have used
Yes, ma'am.
many times. Okay. Therefore, I just pointed out with some tricks only. RAT, RST are the symbols to remember in order to have partial order relation and equivalence relation. That's all for today. We will stop. Tomorrow also we will take some basic notions so that one can understand real analysis 2 part very nicely and smoothly. Okay. Any difficulty in today's lecture? If you have, you can ask me. These are the two homeworks I have given you. 0, 1 uncountable and where it is? Distributive law. I think one can prove De Morgan's laws also as a homework. I want the proof. Okay? Because whenever we were writing the proof of any mathematical statement, we have to think very thoroughly. Okay? Very finely we have to think on the proof. That's why I just suggest you to write the proof as a recon. Okay? So we will stop for today. Thank you for being with me for today's lecture.
मॅम 0 आणि 1 मध्ये असं खूप म्हणजे 0.001 0.002 असं खूप येऊ शकतात ना, त्यामुळे ते अनकाउंटेबलच धरतात ना.
Right, for our understanding it is correct. That is, if I give the counting with two numbers, say, suppose I give 0.1 to be a first number, then can you find the second number? In closed interval 0 to 1, that is not possible, as you have told me. Very correct. Or if I mention 0.1 as first, 0.2 as second, but there are again infinite number of elements between 0.1 and 0.2. Therefore, as of such, we cannot give the counting. We cannot give numbering to the real number set. That's why it is uncountable. You are very correct, Sanjana. You are very correct. But I want the mathematical proof, how the proof of mathematically given. And that was there in your BSc course syllabus books also. Okay? Try for it. If you are not getting the proof, I'll take it in the next lecture. Okay? That's all for today. We will stop here. If you have any queries, you can ask me. If not, let me stop. Thank you.